the turn back on? Okay, so we're going to start with exponents. Square root of x is x to the 1/2. Leave root of x, x to the 1/3. So roots become fractions. 1 over x, x to the minus 1. It's in the denominator, and you bring it up, it has a negative exponent. 1 over x squared, x to the minus 2. Okay, so that's just, you just need to remember that that's how that works. So if we have this, here's some examples. 2 over 3x to the 4th. And I want to write that with x in the numerator to a number. I'm just going to move this. Do I move the 3? The 3 is not affected by that exponent. The exponent only affects the x, the number right below it. So this would be 2/3 x to the minus 1, x to the minus 4. 1 over 4 square root of x. Again, the 1/4 is what it is, so that's 1/4. Square root of x is x to the 1/2. But bring it into the numerator, x to the negative 1/2. Okay? Let's go the other way. If I have 3x to the minus 5, and I want to write it with a positive exponent, then it's going to be 3 over x to the 1/2, x to the minus 1/2. We're going to see this a bunch in this class, this exact form. That's just 1 over 2 x to the 1/2. Or when it comes to actually computing things, it's easier for us to think in square roots, so I would rewrite it that way. Okay. I need to start writing from this side and come this way because I have to stay in here for the video. All right. All right, so now we're going to talk about function notation. I promise I don't write this fast and talk this fast ordinarily. We're just trying to get through a lot of it. All right, so functions. Function notation is this. F of x or f at x, I will usually say of, but at is okay too. Remember that this is your y value. So x is your input and y is the value of the output. So this will give you an ordered pair where the y value is just whatever f of x is. Okay, so it's important to connect x to the input and f of x is your y value. It's important to make that connection. We also have composition. That's where I take, instead of just a simple x, I put a whole new function in as an input. Okay? And it's important that we get this right. We're going to use this by about week 3. So let's look at a couple of examples. So let's say that you have f of x equals 3x over x squared plus 1. All right, let's find f of minus 2. So that means we just put in a negative 2 everywhere we had an x. Anytime you have negative signs, or anytime this is an actual function, I strongly encourage you to use parentheses until you have accounted for everything. So 3 times negative 2, negative 2 squared. So you see, whatever I had the x, I put in the negative 2. So since the x was squared, the whole negative 2 was squared. So I need the parentheses. So negative 6 over 5. So if I said that, then if I wanted to write an xy pair, my xy pair would be negative 2. That's my input. And y would be my output. Okay. And now here's the one. F of x plus h. This does not mean write this down and add a plus h at the end. Right? This says this is the input. Right? This right here is the input, which means it goes in everywhere you used to have an x. So again, parentheses are important. So here I would have 3 times x plus h. Wherever I had an x, I now have an x plus h. And then down here, the x used to be squared, so now the x plus h is squared. So it's important not to just tack that h on the end. It's a change to the input, so it needs to go in for each x. Yes?
Is it okay for us sometimes with the squares, like if they're the same, for us to write it twice?
Yes.
Like just with
yes. So like for this, so for a problem like this, we won't ever use a function as complicated as this when we're doing x plus h's. But yeah, when you want to multiply, at some point if you need to multiply this out, you can definitely write it that way. Yeah.
So like with canceling and stuff, it's just easy.
Yes, yes, yes. Okay, so graphs. You need to know the graphs of a lot of different functions. We're not going to review them today because they're like in the front of your textbook, I think, on the front cover, back cover. Back cover on Vanna, right? So we're not going to cover all those shapes, so I'll let you do that. It is important for all the shapes, when we want to sketch a shape, it is sufficient, say for an exponential, for example, y equals 2 to the x. This is a sufficient sketch. I know it goes through 1 because anything to the 0 is 1. That's enough. We're not looking for perfection until we get to a section where we're actually using calculus to achieve that. So when I say know the shapes, that's as much as I need you to know. X and y intercepts, general shape. Okay. The other thing, though, that is important is, so let's talk about x and y intercepts. Let's do that. Let's just remember how you find those. The y-intercept is always the easy one. I'll often abbreviate it y-int. The answer, we need to get in the habit of all answers that are points need to be an ordered pair, an xy pair, and all lines need to be written as lines. So we need to get in the habit, and then all ranges need to be written in interval notation. Those are just the standard way we're going to report answers in class. So I don't want to see this. Okay, I know what you mean, but really what would be better would be this. Did I do that right? Okay, so the y-intercept happens when x equals 0. It is always easy to find the y-intercept. That's the easiest one always. It's always the first thing you do. Plug in x equals 0, you get the y-intercept. So how do we find the x-intercept?
0 for
Y equals 0. Now, that requires typically then that you solve for x. This one, you put in x equals 0, you just compute. That's easy, right? So this one, compute. This one, you're going to have to solve something. So let's look at an example of that. Trying to stay to the same ones I'm using in the notes. Okay, so if I put in, if I want the y-intercept, right, that's easy. Y-intercept means put in x equals 0. If I put in x equals 0, 0 minus 0, 0, that's easy. Okay, the x-intercept, I need to set y equal to 0. So now that's a polynomial equation. So how do I solve that? Anyone
Count
remember?
common factors.
Yeah, set the x.
You need to factor it. Okay, anytime you have something equal to 0, if you can factor it, a times b times c equals 0. If you've multiplied some set of numbers and they equal 0, what do you know? One of them has to be 0. And so it's important to get the 0 on one side. So factoring it. I really wrote. Can I factor that one? Not with whole numbers. So at this point, now I need to solve it. That means this one is 0, or this one is 0.
Doesn't that need to be x squared on the outside?
Yes, it does. Thank you. That's a very good point. I sometimes make mistakes too. So please thank you for correcting me. Don't let me make a mistake here. All the way down here, and they say, but wasn't it supposed to be? Yeah, I'm not embarrassed by that. So please, yes, thank you. All right, so this is even better because this is the reason I made it this way. X squared equals 0. What's the answer to that?
X equals.
X equals 0. And then this one is, of course, x equals 2. Do you need to write all of this? Not for me. So for me, once you got to this point, if you just simply said 0, 0, and 2, 0, that's simple enough that if you need to write this, please do. If you don't need to write it, this is basic enough that you can go straight to the answer. I don't need to see every last detail of work. But if you need to do it, please write it out. I know at some point we get in the habit of thinking, oh, if I don't write it down, that means I'm smarter. When you get to calculus problems, they're involved enough. Write out the steps. Don't carry it all in your head. You'll have better success if you write things down in kind of a systematic way. Okay, so x-intercept, y-intercept. What else are we interested in with graphs? Domain. So let's talk about domain. Domain is basically all the legal x values. Every x value that can go in. Okay, so these are x values, that are allowed to go in. So where do we have a problem? Let's look at this one. Are there any x values that cannot go in this? I can cube or square anything, right? So this one, the domain for that is all reals. So if I had y equals x cubed minus 2x squared, I will often write d colon, and I'm okay with all reals, some sort of funny r, or in interval notation, negative infinity to infinity. So polynomials, no problem. What about exponentials? Is there any value that you can't put in that exponent? You can put in anything. So this has all reals. So where would I find something where I can't do something? What can you not divide by?
0.
0. So if I had this one, we'll get to that one in a minute. What about square roots? What can I not take the square root of? Negative number. So if I started with this, what do I know? I know this part, and this is, I encourage you for domains to write an equation for the domain, then solve for your x. Don't try and do it in your head. What do I know? I know this. That number in there has to be what? It has to be positive, or can it be 0?
No.
Actually, it can't. Square root of 0 is 0, so that's okay. It just cannot be negative. But now I have an equation I can solve, right? And then I can solve it and get my domain. What about this one? What can I not divide by? 0. So I know wherever the denominator is 0 is not in the domain. So where is the denominator equal to 0?
2.
Yeah, 2 and negative 2. So there are two ways to do that. You can either do the intermediate step of x squared equals 4, and just remember when you square root it's plus or minus. Or how does this one factor?
X plus 2, x minus 2.
Yeah, x plus 2, x minus 2. And that would give, so either way you get those same plus and minus 2. So these are not in the domain. So how would I write the domain? Kind of the shorthand sloppy way is to say, well, x cannot equal plus or minus 2. Well, the more correct way is
Negative infinity,
negative infinity up to negative 2 together with, that's the u, together with negative 2 up to 2, have to hop over that, together with 2 to infinity. Clearly much shorter. I'm okay with this over this, but this is technically sort of more formal English, if you will.
So like on a test, would you prefer that over that?
On
Or
a test,
either way?
on a test, I would probably prefer this one because on a test, I'll be clear, but I would think on a test I would prefer this just because I don't want you to spend a lot of time thinking about this because this is not calculus. So, I tend to try and make my tests so that the numbers work out nicely because I'm not interested in how much computation you can do under time pressure. That's not what this class is about. So I tend to try and make the test problems work out simply. I mean, once you've done the calculus correctly. Okay, so this brings us into rational functions. So let's be thinking about this one. How are we doing for time? I know. So we have just covered up through the first month of pre-calculus, I think. So now we're heading into rational functions. So this is a rational function. So a rational function is it comes from the word ratio, right? Ratio means fraction. So rational function is just a ratio of usually polynomials. Doesn't have to be, but that's what we'll be doing. So we already know that these two numbers, x equal plus and minus 2, are not in the domain. We cannot divide by 0, and that would give us 0. Now, those two exceptions can be one of two things. We have what are called holes, and we have vertical asymptotes. Both happen. The denominator has to be 0 for either one of those to happen. So what's the difference between them? just, so I know people are used to thinking, oh, wherever the denominator is 0, that's my vertical asymptote, mostly. The thing that we need to do first, anytime you see something like this, is to factor. So when we factor this, what do you see?
Cancel out.
Cancel. These ones right here that cancel, that is a hole in the graph. Okay, so in this case, a hole is where factors cancel. I'll just write it that way. And we're going to get to that next week, what happens at that hole. So remember what a hole in the graph is. A hole in the graph is just, you have a line going across and then there's a point at which it doesn't exist. Okay. So that part, anything, you have to do that part first. So now there's a hole in the graph there. So now what is this x plus 2? What's left are the vertical asymptotes. So after you have done this step, it's where the denominator is equal to 0. Okay, so in this case it would be x equals -2. So again, you could write vertical asymptote equals -2. I know what you mean, not a good way to write it. Vertical asymptote is a line, so go ahead and write the equation of the line. That's a vertical line. Okay, so let's just do a quick sketch of what this looks like. Actually, this is a harder quick sketch because it's got a variable on the top. I think, if memory serves, it looks like this. Is that right? No. I can't remember off the top of my head, but this is a great example, great time to show you Desmos. And then, all right, so I'm going to come back and do this with Desmos, but that's going to put a big glare on the video camera, so I'll come back and do that at the end of the class. I'll show you, that's a great time to show you Desmos. Okay, so just remember for rational functions, holes first, and then vertical asymptotes. We're going to use this importantly next week, so good to get a handle on that. Okay, so let's look at a few more graphing things. Are you guys getting lulled to sleep? Is it time for Precalculus Pilates? Let's do it. Everybody stand up. No, I'm not kidding. I'm going to do this on camera. So, parabola. Cubic. Oh wait, I did this right. I got to do it backwards for you guys, right? Cubic, right?
Oh, yeah.
Exponential.
Is it V?
No, exponential was this one. So wait, this way for you. Log. Do you remember the shape of the log?
It's like yoga class.
I know, yeah, exactly. Wait, what else do we have?
Rational.
Rational.
Squares.
Oh, how do we do
Either
it?
that one, just a straight arm.
Oh, the square root,
That's rude.
right? Square root? Yep. But, oh, straight line? Yeah, you may sit down. Okay. All right, so we've got holes and asymptotes. All right, so now let's talk about transformations. We just did all those shapes, right? Now we're going to take those shapes and move them around the graph a little bit. In Precalculus, you did a lot with complicated transformations. We're not doing that here. It's just, again, helpful sometimes if you want a quick sketch to know kind of quickly how to get to it instead of having to plug it on a calculator or a Desmos. So let's just look at a few transformations. The important ones that we're going to deal with are reflections and vertical shifts. Okay, so the only reflection we're really all that interested in is y equals negative f of x. So an example would be y equals negative x squared. Right, we know x squared, so negative x squared is what? Right, it just reflects down. Vertical shift, that's where you simply add some number. And we're going to use c to represent some number. We're going to do that a lot in this class. So, and then we may find it later or we may not. An example would be x squared plus 2. So just take your x squared plus your x squared and just everything shifts up by 2. So that's the first one. That's the second. And if I were fixing this, I would just go, and that's close enough, right? I say, you know, a lot of times I draw it first and then put the number in. So really, when we're sketching, for just sketching, this is about as good as we need to have. So don't panic about trying to get it all perfect. Now, the last one that does give people some trouble sometimes is piecewise functions. So let's talk about a piecewise function. Does anybody still, it used to be this way, does anybody still have a cell plan where, or anyone who's been, you guys taken an Uber before, or a taxi, a cell plan, you pay a fixed rate, and then anything over you pay per mile, per minute, right? That kind of thing where you pay this much here, but then once you, so let's look at a cell
Like
plan.
a marginal tax rate.
Yes, who said that? Yes, marginal tax rate, yes. Let's look at a cell phone plan. So, I have, 6 in capital G, that's plan 6 gig, right, for my cell plan that I share with my son. We just got the message, 90% usage. Fortunately, it rolls over today, so good news for me. But if it hadn't rolled over, then I might pay per amount over that I use. So in this case, I would have, this is a flat rate. As long as I use anything up to that, it's a flat rate. But then, as soon as I go over, now I'm going to pay per. So I have 2 different rates. One's here and one's here. So it's a piecewise function. If I'm in this piece, it looks like this. If I'm in this piece, it looks like something else. Right? So these are piecewise functions. Marginal tax bracket is an excellent example of another one. So let's look at this one. If I have y equals x plus 1 for x less than 0, and negative x squared for x greater than or equal to 0. If I'm in one piece, it's defined one way. If I'm in another piece, it's defined another way. So if I wanted to know what is the value when x is equal to 2, which piece would I use? Right? I find, well, it's not less than 0, so I'm in this piece, so I use this definition. So for here, y would be equal to negative 4. So the important thing about piecewise functions is different definitions for different pieces, for different sets of x values. So if I wanted to graph this, my breakpoint is here. That is not a vertical asymptote, right? Just so we're clear. Negative, let's do that one first. Negative x squared. What do we decide that looks like? Parabola, upside down. Is it shifted? No. So it's going to look like this. But is it good for the whole time?
No.
No, it's only good for the positive x's. So this one, I need to take off. It's not good for that. Is this point on the graph? X equals 0. Yes, this point is on the graph right there. Okay. Now let's look at this one. X plus 1. That's a line shifted up by 1, which means it's y-intercept. This is nx plus b4. Y-intercept is at 1. Is there a point there?
No.
Right? 0 is not in that piece. So I know it's headed there, but it doesn't get there. And positive slope of 1. So the important thing about piecewise functions is different definitions on different pieces. So just identify your piece and draw that. Identify your piece and draw that. And if it helps you to draw the whole thing of it, and then just erase the part that you don't need, that's okay too. So here's a line, but it's only good for x less than 0. Here's a parabola, but it's only good for x greater than or equal to 0. Okay. All right. Okay. You need to get up again? Oh. All right. Let's look at exponentials and logs. I might actually get through all of this. I'm very excited.
We have about 5 minutes.
Thank you. Yes, look at that. All right. So exponentials and logs. So let's start with logs. We need to remember laws of logs. Again, we're not doing, in pre-calculus when we covered this, you did very complicated things that you were trying to simplify or pull apart. Here we're not going to do very complicated things. We've already covered that part, but we're going to need to be able to use these concepts to simplify things to do calculus. So the one you need to remember, so let's do 2. So we tend to write it log base b of x. Log of x means what? What's the base if you don't write it?
10.
Then we also have one called log base e of x. And you'll remember that that len or line or ln, I usually say len, but any of those are fine. Len x. So if you see len x, you know it's base e. If you see log x, you know it's base 10. If you see a number, you know that that's the base. Multiplication on the inside becomes addition on the outside. Division on the inside becomes what on the outside?
Multiplication.
So division
Minus
becomes
Subtraction.
subtraction. Yep. So addition, multiplication goes to addition, division goes to subtraction. That kind of makes some intuitive sense in terms of, I think of addition and multiplication as both increasing, and division and subtraction as both decreasing. And then the last one that we're going to use a lot, let me make sure I get this write it the same way. If I had something raised to an exponent, this exponent I can pull down in front. So m log a. Okay. So the idea is to use these to rewrite logs into simple logs, because those are things that we will know derivatives of when we get there. So here's an example. If I had log 2x, that's multiplication on the inside, so it becomes addition on the outside. So log 2 plus log x. That's a simple log. Log 2 divided by x becomes log 2 minus log x. The part that's in the denominator is the one that has the minus. So log 2 minus log x. Log x squared. Where can that 2 go?
2 log x.
Down in front, so 2 log x. What about this one?
Can't touch it.
Nothing. We can handle multiplication, division, and exponents. That we can't change. We can't fix
It's
that.
already simple.
There's nothing more you can do. It's similar to this. Square root of 4x I could write as square root of 4 times square root of x. I can break those apart. Square root of 4 plus x you cannot break apart. Okay. Another good example, let me just bring this up while we're talking about this. 1 over 4x. That's right. X over 4x. I could write, let's see how I'm trying to, all right, so this. Nothing cancels here. X over 4 plus x, nothing cancels here. You can only cancel multiplied factors. This 4 plus x, just like here, denominator, square roots, and logs, you can't break that apart. It's wedded together. There's nothing you can do. So these absolutely do not cancel. What about these up here?
Yeah.
Yes, multiplied factors you can cancel. When I cancel them, what do I have left in the numerator? 1. So this is 1 over 4. Okay. Right, so, perfect.